We're kicking off today with an opening keynote from Sergey Levine, someone who probably needs no introduction in the RL community. He's an associate professor in the Department of Electrical Engineering and Computer Sciences at Berkeley, where his research focuses on machine learning for decision-making and control, with an emphasis on deep learning and reinforcement learning algorithms. And he's interested in exploring how learning can be used to acquire complex behavioral skills in order to endow machines with greater autonomy and intelligence. He's published works in many of the top academic journals in the ML and AI space, and he's also routinely featured in many top mainstream publications, including the New York Times, the BBC, the MIT Tech Review, and Bloomberg Business. Today, he'll be talking about the emerging field of offline RL, which allows one to leverage large previously collected data sets to build better RL agents. And he'll also be covering the technical foundations of offline RL, which is great because I don't know much about it, and discussing recent algorithm advances and present. He'll also be presenting several applications. So this sounds super exciting. Welcome, and we're excited to have you here too.
All right, thank you for the introduction. All right, I'll start with a kind of a big picture question. What makes modern machine learning work? At a very high level, we could say that a lot of what makes modern machine learning work is the ability to utilize very large data sets and combine them with very large high-capacity models, transformer models, big ResNet models, that sort of thing. And there's a lot more, of course, that goes into it, a lot more technical stuff that you have to know to get this right. But with these two ingredients and a bit of care, you can get very good results on image recognition, translating text, recognizing speech, all sorts of applications that are basically kind of perceptual recognition tasks. Now, a lot of these domains involve us making some assumptions that make them easy, that make them manageable with standard supervised learning methods. For example, we might assume that our data points are independent of one another, that the output for one input doesn't influence another one, and that the ground truth labels are provided to us at training time. These are kind of standard assumptions for supervised learning methods. Now, many domains overtly defy these assumptions. So if you're controlling an autonomous vehicle, of course, your outputs do influence future inputs. If you're controlling a robotic arm, the data points are not independent. If you're doing inventory management to maximize profits, you might not have ground truth labels that tell you how to adjust inventory levels. You need to figure out how to do it. If you're trading stocks, again, same deal. So a lot of these domains, these are control-centric domains that don't fit into these assumptions, and we all know that. So decision-making problems often don't satisfy these assumptions because current actions influence future observations. The goal is to maximize some utility metric like a reward instead of just to match a ground truth output, and optimal actions are not provided. Okay, that's all fairly basic stuff. However, I would say these are not actually just issues in control. In many cases, I would say even in most cases, real-world deployment of machine learning systems, even the supervised learning systems listed above, has these kinds of feedback issues. Here's an example. Let's say that you're building an app to predict traffic. Let's say your Google Maps or something of that sort. Well, you might think that that's a supervised learning problem because you get training data of traffic and you learn to predict traffic based on previous features. But then people are going to use your app to make decisions, and they're going to choose where to drive or not drive, depending on whether you predict there's traffic there. So now there's a feedback problem. Your outputs, which you think of as predictions, but they're really actions, influence your future inputs because they'll determine where people will drive. And if your app doesn't take that into account, then it'll make mistakes. In fact, I would say that most deployments of machine learning systems in the real world have these kinds of feedback issues. We just usually sweep them under the rug if we're doing supervised learning. So if ultimately machine learning is always about making a decision of some sort, why don't we treat every machine learning problem like a reinforcement learning problem? Well, the issue is that it's darn inconvenient to do that. And that's because reinforcement learning is really two different things. First, it's a framework for learning-based decision-making. It takes us from a paradigm where we think about models that map inputs X to labels Y into one where we think about models that map states or observations to actions, to decisions. And those decisions then have consequences. They affect future states, and we have to reason about long-term utility maximization. And as I tried to argue on the previous slide, most deployments of ML systems actually look like this. But reinforcement learning is also something else. It's a framework for active online learning for control. So this is the classic picture from the Sutton and Bardo textbook that describes reinforcement learning as an active online process where an agent interacts with the environment, collects experience, updates its behavior, and so on. You can think of this visually like this. So you've got your little agent, your robot, it interacts with the world, gets a little bit of data, uses that little bit of data to update its policy or value function, and then interacts with the world some more, throws out that data, gets some more data, and repeats this many, many times. And that's very appealing to a lot of people because it kind of looks a little bit like the way you might imagine that a person or an animal might learn. But it can be very difficult to deal with in complex high-stakes environments like inventory management or stock trading. So number one, the framework for learning-based decision-making, almost all real-world learning problems look like this. So we would really like to have something that can handle the challenges of decision-making. But for number two, almost all real-world learning problems actually make it very difficult to do this. They make it very difficult to do active online learning when, for example, deploying an untrained policy to do inventory management for your multinational corporation can result in you losing billions of dollars in just the first hour. So you don't want to do active online learning for autonomous driving. You don't want to do it for stock trading. You don't want to do it for inventory management, at least not from scratch. So basically what this talk is about is how you can get one without having to do two. Okay, now as an aside here, some of you might be wondering, okay, maybe I'm making too big of a deal out of this, right? Like, doesn't RL kind of work? Like, aren't there all these cool results that use RL? Well, let's look at some of these things. So here I have some pictures on the left. Some of these are things you might have heard about, some of them less so, depending on your application area. But we've seen RL work really well in domains from playing video games to controlling robotic systems to beating the world champion at Go. And that's very impressive. On the other side, though, supervised learning systems have been very successful in settings that we would characterize as open world settings, recognizing the class of any image on the internet, translating any text, recognizing any speech. And there's a big gap between the stuff on the left and the stuff on the right. The gap is not so much a gap in terms of task difficulty, it's a gap of task diversity. It's a difference between closed world and open world environments. The bot that's playing Go needs to be very good at playing Go, but it doesn't need to worry about someone spilling coffee on the Go board and having to figure out how to deal with that unpredictable situation. In open world environments, these kinds of methods are much harder to use. And it's pretty clear to see why. If you imagine that you need an ImageNet scale data set to learn to generalize to your open world environment, and you have to recollect the data each time you update your model, then we're really talking about recollecting an ImageNet scale data set each time you update your model. And that's, of course, never going to work. All right. So how can we make RL look more like supervised learning? In the sense that we still wanted to be able to handle all the requirements of a decision-making system, but we don't want it to require this online active data collection. We want to be able to do RL off of previously collected data sets, just like we do supervised learning using ImageNet or large textual data sets. All right, so these are the two things from before. I just swapped their order, so now the online part is on the left. And classically, we think of RL as on-policy RL. So you collect some data, update your policy, and then repeat. And what we're going to try to do is offline RL. So offline RL basically deals with a setting where some other policy that you have no control over, pi beta, has collected data before. And that data goes into a buffer that we're going to denote D. And that buffer is going to be used to learn the best policy you can get. And that policy has to be learned using only D without any additional interaction with the environment. And once you've learned it, you deploy it in the environment. Of course, in reality, you might go and fine-tune it further. But the main focus of today's talk is how to get that fully offline stage. That's usually the hard part. Once you can train a decent policy off of the data set D, then you can deploy it and fine-tune it just like with any other RL method, and that's not particularly difficult. All right, so the offline workflow then would look something like this. Step one would be to collect a data set using any policy or mixture of policies. So that's pi beta. And typically, the algorithm does not assume that it has control over what pi beta is. Pi beta is basically the source of data, and it could be anything. It could be humans performing the task. It could be an existing system performing the task. It could be random behaviors, or it could be any combination of the above. So It's okay to just mix things, whatever process you can get to collect data, that's what you've got. And this is only done once. So in the same way that like the ImageNet data set was only collected once and then it's used by everybody, step one should be done once. You can go out and collect more data if you want more data later, but you would just append it to the data you already have. Step two is run offline RL on this data set to learn a policy. And you could think of this as sort of squeezing out the best policy you can get out of the data. Step three is to then deploy this policy in the real world. And if you're not happy with how well it does, you can modify your algorithm or adjust its hyperparameters and go back to step two, reusing the same data. So this kind of paradigm could then be used for settings where online active interaction is impractical. For example, where the stakes are really high, where untrained policy should not be allowed to explore willy-nilly, or settings where it's just very costly to do that online interaction. Things like inventory management, writing drug prescriptions, scheduling the course of scientific experiments, managing power grids, or controlling robots. All right, so why is offline reinforcement learning difficult? Like, why can't we just use regular off-the-shelf RL methods that we already know work in the online regime? Well, I'm going to talk about much more technical reasons later in the talk, but intuitively, the fundamental problem is that offline RL requires resolving counterfactual queries. So let's imagine that we're trying to do offline RL for autonomous driving. And we have training data where humans drive cars on roads, and humans are not perfect drivers, but they're pretty good. So maybe humans are not optimal. They're not going to change lanes in the most efficient and safest way, but they're not going to do silly things like just drive off the road. So generally, if they're on a straightaway, they're going to stay straight. During offline reinforcement learning, the policy needs to figure out, you've never seen somebody just turn left and swerve off the road before. Is that a good idea or not? Now, that kind of seems like a silly question to us. Like, of course it's a bad idea, but the policy has never seen it. Like, you know it's a bad idea to swerve off the road because someone told you, like, yeah, if you crash your car, like, bad stuff happens. No one told the policy this. All it ever saw is humans driving cars in normal, reasonable ways. So how do we know if this is good or bad if we didn't see it in the data? Online RL algorithms don't have to handle this because they can simply try this action and see what happens. So an online RL algorithm will actually crash the car, and from that it will learn that that's a bad idea. Offline RL methods have to somehow account for these unseen or out-of-distribution actions, ideally in a safe way. But at the same time, they still have to make use of generalization. They still have to come up with behaviors that are better than the same. So you have to allow them to generalize, but the same things might happen. So that's kind of a delicate trade-off. All right, so what do we expect offline RL methods to do? Like, if we can't allow them to go out of distribution, how are they going to help? Well, so one bit of potentially bad intuition is that it's like imitation learning. Okay, so you've got your data, and what you're going to do is you're going to try to copy that data to get a policy pi theta that does just what the data did. I think that's bad intuition because offline RL can do a lot more than that. That said, it can actually be proven that under some circumstances, even in this setting, offline RL is actually better than imitation, and we have a paper on that called Should I Run Offline RL or Behavior Cloning? That's in iClear 2022. But I think the much better intuition, the kind of setting where we really expect to see a lot of benefit from offline RL, is a setting where you have highly suboptimal data, and you can kind of think of the policy as pulling out the best thing that you can do by combining parts of the data. So one kind of very simple intuitive example of this is this stitching example. If you've seen data of going from A to B, and you've seen data of going from B to C, you should be able to figure out that you can go from A to C. So that's an inference you can make using the data, and offline RL methods should be able to do that. But it actually goes further than that. That's simply the clearest example. You can imagine a setting where this stitching behavior happens all the time at kind of the micro level. So imagine, for instance, that you have data from humans trading stocks, and each of the stock traders is good in different circumstances and bad in other circumstances. So none of them are perfect. None of them are good everywhere. Well, you could imagine an offline RL method that sort of figures out how to be the best of the best human in each situation. But overall, that would be a lot better than any one human could be by themselves. So if you sort of combine the best parts of the data everywhere at this micro scale, you can actually get a behavior that is a lot better than, for example, the best person that was responsible for collecting the data. So if we have algorithms that properly perform dynamic programming, which I'll discuss, we can take this idea much further and we can get near optimal policies even from highly suboptimal behavioral policies, even from highly suboptimal data. Here's an example from a paper that we wrote a couple years back called COG. This is led by Avi Singh, that illustrates one of the things you can do with offline RL. And this is a robotics example. So let's say that you have this task where you have to pick up a ball from a drawer. And you have some data of the robot picking up the ball from the drawer, and you can use it to learn this task. But then at test time, the drawer will be closed. Okay, so it's kind of like a common sense example. A person would have common sense. They would figure out that, like, hey, my job is to pick up this green ball. The drawer is closed. What do I do? Well, you go and open it. But of course, the robot can't figure that out because it's never seen a closed drawer before. It has no idea what to do with this. So it would fail. But now imagine that just like a person has prior experience of all these other things from their lifetime, let's say the robot also has a prior data set of a whole bunch of other things that could be done in this environment. Now, none of these things actually involve performing the desired task. None of these things involve picking up the ball. But they involve other behaviors like opening drawers, closing drawers, moving objects around, that sort of thing. If we run offline RL and we simply combine the prior data and the task data, we simply put them into the same buffer, assigning a reward of 0 to all the prior data, the offline RL algorithm should be able to figure out that the state where the drawer is open has a high value because you can pick up the ball. Therefore, any state in the prior data that resulted in the drawer being open also has a high value, and therefore anything the robot did leading up to that state also has a high value, even though it has never done those things together. It's never opened the drawer and then picked up the ball, but it can figure out with dynamic programming that these things relate to one another. So that means that if you run offline RL on this, combining the prior data and the task data, you can pick up the ball from an open drawer, but you can also open the drawer and pick up the ball if it starts off closed. And you can also close the top drawer, open the bottom drawer, and then pick up the ball. And if there's an object in the way, you can lift the object, put it away, and then open the bottom drawer, and then pick up the ball. So you're stringing together all these behaviors, even though you've never seen them perform together. All right, let's talk about some technical materials. So before I explain some offline RL methods, let me just give a quick primer on off-policy RL. So those of you that are familiar with Q-learning will basically know all this, but just to get us all on the same page, in reinforcement learning, you have an agent that takes actions. We denote those with A, and the world responds with states S, and the resulting reward R of S comma A. The goal in reinforcement learning is to select a policy, pi of A given S, that maximizes the expected cumulative reward. So the total reward that the agent will get if it runs that policy for an entire episode. The Q function is a very useful object. It depends on the policy, and the Q function quantifies what is the total reward you will get if you take the action AT in state ST and then follow the policy pi thereafter. So if you can learn the Q function for a particular policy pi, then you can recover a new policy that is as good or better, usually better, by taking an action with probability 1 if it is the argmax of Q pi. And this is the basis of policy iteration. You can also skip the middleman and try to directly learn the optimal Q function so that its argmax policy is the optimal policy. And you can do that by minimizing the difference between the left-hand side and right-hand side of the Bellman equation. So if you ensure that QSA is equal to RSA plus the max over the next Q value at all states and actions, then the corresponding argmax policy will be the optimal policy. And that's the basis of Q learning. So if you can enforce this equation at all states, you get the optimal Q function. So what we typically do for Q learning is we subtract the right-hand side of this equation from the left-hand side and minimize the difference at sampled states and actions. So here, SI, AI, and SI prime are samples from a data set, from a replay buffer. Okay, so in principle, this can now be used as the basis for an off-policy RL algorithm. Also the basis for an offline RL algorithm. You could simply take log data without collecting any additional data and try to minimize the left-hand side, the difference between the left-hand side and right-hand side of this equation. And that would be a viable way to get started. But by itself, this isn't quite going to work. Okay, what's the problem? So we tried to basically run this kind of naive procedure a few years back and to see what would happen. and we used the half cheetah benchmark. And what we saw is that performance starts to go up a little bit, but then it quickly drops. And it looks a lot like kind of overfitting, right? That's kind of what you'd expect if you had really catastrophic overfitting. So we try to vary the data set size. So here, blue shows a data set of 1,000 data points, red is 1 million. And you can see that there's basically no difference. You don't become better as you add more data, which is strange. Like you would expect if it was overfitting that this would fix it. So then we try to see how well does the Q function think it's doing. So if we actually query the Q function itself for the estimated values, the y-axis here is a log scale. It thinks it's going to get 10 to the 7th power. Whoa. So it thinks it's going to do really well, but it ends up doing terribly. So we're getting massive overestimation. Why is that happening? Well, the issue basically comes down to something called distributional shift. So if we take this Bellman backup and we rewrite it in a slightly different way, we can write it as the expected value of the target Q function under some distribution pi nu. And pi nu is going to be that argmax distribution. What is our objective for training the Q function? Well, the objective is to minimize the difference between the left-hand side and right-hand side, but under a training distribution pi beta. So we would expect when we do this that we would have high accuracy under pi beta. But of course, pi nu and pi beta are not equal. The whole point is to find a pi nu that is better than pi beta. So we're experiencing distributional shift. Even worse, pi nu is selected to maximize the expected value of Q. That's a lot like what you do if you want to get an adversarial example. Essentially, pi nu is trying to find an action that will trick the Q function into outputting a large number. And we know from the study of adversarial examples that if you want to trick a Q function, or any neural net, it's not that hard to do. You'll find that adversarial example that tricks it into outputting the value you want, in this case, an erroneously high value. So that's why we see this massive overestimation is due to distributional shift. We have to somehow address this if we're going to get effective offline RL methods. So one of the methods that we've developed for doing this is called conservative Q-learning. So the aim in conservative Q-learning is to directly repair these overestimated Q values. So let's imagine that this green curve is the true function, and the blue curve is your fit. So the blue curve is a pretty good fit to the green curve, but if you try to maximize the blue curve, if you try to maximize the Q function, you'll find exactly the place where it makes the largest error in the positive direction. So the idea in conservative Q-learning is to directly repair these mistakes. So what we're going to do is we're going to have an objective where we've got our regular Bellman error minimization, just like before, and then we have a regularizer. And what this regularizer tries to do is it tries to find a distribution mu that maximizes Q values, and it tries to minimize the Q values under mu. It's a little bit like a GAN in that sense. So what that's going to do is mu will identify those peaks, the largest peaks, and then the Q function optimization will push them down. Now, of course, this won't result in getting the right Q value at those out-of-distribution actions because you don't know what the right Q value is, but it will result in those out-of-distribution actions not having the largest Q value. So then hopefully one of those actions that is actually supervised will be the better one, or something similar to it. In fact, it's actually possible to prove that conservative Q-learning will result in Q functions that lower bound the true Q value. Now, in reality, we use a better lower bound where we also push up on samples from the data. And this might seem counterintuitive because if we're trying to avoid overestimation, why would we push up on samples from the data? But imagine that all of your good actions are actually close to the data set. Then these two terms will essentially cancel out. So if good actions are out of distribution, the first term pushes them down, and the second term pushes up on something else. And then all the good actions become in distribution, and then these two terms basically balance out. And now it's not a pointwise guarantee anymore, but you're still guaranteed to lower bound the value under your learned policy, which is all you really care about. The bound actually holds in practice, so you can actually measure it with Monte Carlo estimation and find that conservative Q-learning always results in underestimation, and there's less underestimation if you use the version with both terms. So that's the CQL-H variant here. And it performs pretty well in practice. So these are older results at this point. They're a few years old, but across a range of benchmark tasks, CQL tends to attain very good results. Now, since then, better methods have come out. So back when this first came out, it was a lot better. But for the methods that came out since then, there's been quite a bit of work on methods that extend CQL. And there's been a lot of growth in offline RL methods, and CQL has been very widely used. So these are just a few papers that have come out that show that, yeah, CQL actually still works pretty well on new tasks, and you can extend it in various ways with things like data augmentation and get even better results. But the thing that I want to conclude on is a little bit of a discussion of applications that perhaps illustrate some of the power of offline RL. So in my research, I do a lot of work on applications of RL to things like robotics, and the process for doing that with online RL has always been quite painful. So typically, you first have to instrument the task so that you can run RL, add safety mechanisms, autonomous collection, rewards, etc. Then you wait a really long time for online RL to run, and then typically it doesn't work on the first try, so you change the algorithm in some small way, and then you wait a really long time again. And once you're done with this, even if you're successful, you have to throw it all in the garbage and start over for the next task that you want to learn. So that becomes a very onerous process if you're actually doing RL in the real world. The offline RL process is to first collect your initial data set and train a policy on that data set. Now, again, it doesn't always work, so then you change the algorithm in some small way, but you don't have to recollect the data. You just rerun the training process the same way that you would with supervised learning. And if you do want to collect more data, you simply append it to the data set, so you don't recollect it all from scratch. And when you're done with this, you can keep the data set and use it again for the next project, which is also really powerful. So I'll tell you about a couple of settings where we've used this power to make it a lot easier for us to make research progress. So we've been doing a lot of research at Google on large-scale robotic reinforcement learning using real-world data. So most recently, we had this project called MTOpt, where we collected a huge data set of multitask behaviors, 12 different tasks, thousands of objects, months of data collection. And then we had a new hypothesis. We thought, well, can we learn these tasks without rewards using goal-conditioned RL? Now, this talk is not about goal-conditioned RL. I just want to make the point that we could answer this hypothesis with offline reinforcement learning without any new data collection. So we wanted to see, okay, if we give the robot a goal image, can it learn to reach that goal image without any hand-designed rewards? So we reuse the same data that we'd used for these other projects, and then just change the algorithm to a variant of CQL with goal images. And we could immediately actually get policies that could succeed at the task to resolve our hypothesis. In this method, there's no reward function. Tasks are defined entirely using goal images. It uses a conservative offline RL method similar to CQL and works very well as an unsupervised pre-training objective. You can think of it almost like kind of a BERT for robotics. You train the goal conditioned Q function with unsupervised offline RL, and then you can fine tune it with a task reward much more quickly. So the point is that we could resolve this without any new data collection, just using the data from these other projects. Another example, in early 2020, my student Gregory Kahn collected 40 hours of a ground robot, think of it as kind of a delivery robot, driving around different environments. In late 2020, Dhruv Shah could use offline methods to use the same data set to train a robot that could deliver to target locations, and in 2021 extend this method further to get a robot that can search through novel environments to find objects that it hasn't seen before, again using all the same data sets. Now, there are many other topics in offline RL that I don't have time to cover. Model-based learning is a really good fit for offline RL, so generally you can do some really cool stuff there. A lot of ideas in CQL actually transfer to the model-based setting, but you can also use huge models like transformer models. Those work great for offline model-based RL. So for that, you can check out the paper called on the trajectory transformer. Multitask offline RL, there's really interesting stuff you can do there, incorporating data from other tasks, and many more. But the main takeaways I want to leave you with is that there's still a considerable gap between current offline RL methods and kind of the dream of offline RL that I presented. So if you're interested in doing more work in this area, there's a lot of work to be done. Developing workflows for offline RL. In supervised learning, we have this training test split. What's the equivalent of that in offline RL? As a starting point, we have a paper that provides some ideas, but a lot more work is needed. Statistical guarantees, guarantees about distributional shift, guarantees about safety, as well as scalable methods and large-scale applications. I talked a lot about applications to robotics, but I think these methods can be applied very nicely to lots of other domains, from inventory management to power grids to dialogue systems. And I think exploring application of scalable systems is a really promising future direction. All right, so I'd like to thank, of course, the students that carried out much of the research that I discussed, and I'd like to thank you for listening.